Westinghouse is a failed company. They're now CBS.
You just keep spinning something around and around and around and around in a circle. That centrifugal force is going to drag it outwards.
The turbine only goes as far as its material will allow.
Welcome to Supply Chain. I'm Tim Culpin of Culpium.
And I'm John from Asianometry.
John, you've done 4 videos at Asianometry on turbines.
Isn't that a spin?
That is a spin out. So turbines, I think that's pretty hot, man. I think it's cool that turbines are so hot.
I got into this because people kept telling me that turbines were out. They're all the because this America is
De-industrialized.
Industrializing again, that we need all that power for data centers because apparently there's only one thing we need to make now. And then but then one of the bottlenecks is power. Some people say it's chips, some people say it's memory, some people say it's power. Nobody knows anymore.
It's actually land where people are allowed to build data centers.
It's actually walruses to help fund the energy.
But your latest video, John, was out recently. Gas turbine blades and their heat-defying single crystal superalloys. Love that. That makes me think of semiconductor silicon wafers.
It actually does, and it's actually quite similar.
Oh, well, I stumbled into that. Tell me more.
I mean, there's so many different types of turbines. Actually, there's only 3. There you have steam turbines, jet turbines, and gas turbines. And then there's another one called combined cycle turbines, which combine gas with steam for additional efficiency goodness. And efficiency is the sense of how much energy is coming in, how much electricity you're turning that into, how much of the electricity of the heat energy going in you're going to turn into.
I would assume that the steam turbine was the first one invented. Is that right?
Yeah. And then I think the jet turbines came next, and then they developed the gas turbines out of that. But I don't fact check me on that.
Oh, that's interesting. So everyone probably learnt this in high school, but give us the rundown of the basics of how a turbine works, starting with a steam turbine.
Actually, I didn't know this in high school. They didn't teach me this. They taught me less important things. I think generally you think of these turbines as engines, heat engines, right? Heat comes in, it spins, it turns a thingy, and then with fan blades and all that, and then heat comes out to some extent. I'm sure someone's going to get really mad that I simplified it to that, but it's generally what it is.
Supplychainpod@gmail.com. Get mad.
Send all of your angriest emails. No, do not do that. Efficiency. A lot of this is about efficiency. So these companies, they want a very efficient turbine because that means that their customers, which is the utilities, they have to buy fuel. So they have to buy fuel like gas or oil or coal. Right. And the cost of the fuel is their single biggest operating cost. So when you are efficient, you can get more energy out of that coal or that gas or that oil. And so that efficiency is correlated to the the difference between the input temperature, like the temperature of the gas or the heat going in, and what's coming out. Unfortunately, what's coming out is fixed. It's kind of set by the environment. So if it's pretty hot, it's you can't really change. You can't make it colder, right? So the core thing is heat. So input. So how hot can we get this input stuff? And so which means that these turbines have to kind of the blades and the chambers of these turbines have to sustain temperatures, which can be very, very high. And that's the problem because the turbine only goes as far as its material will allow it to be. It's not just heat, but it's also pressure. Right. Because as you get hotter, you also want to pressurize it because at some point water boils. Or in the case of a steam turbine, the water will boil and you have
liquid to gas. Yeah.
Liquid to gas, and then you're not really going to it's not going to get any hotter. So you put it under pressure, and then it gets super critical, which means that you can pump a lot more energy, you can make it a lot hotter, and it just skips the boiling phase, just goes straight to gas. So anyway, my main point is that with these turbines over the decades is that can the material handle higher temperatures
and higher pressure
over the span of 20 years,
right,
and not like break or not, more importantly, deform. And that's the key thing, right? They have this something called creep, where the blade metal essentially stretches over the span of 20 years.
Interesting. I guess, is that because of centrifugal force and heat? You just keep spinning something around and around and around and around in a circle. That centrifugal force is going to drag it outwards.
You nailed it.
And then you put heat into it, which melts metals.
Or weakens it.
Weakens it.
Yeah. And then in the case of steam, gas is different, but steam is like you have the corrosion effect from water and steam and all that. So
do you need to have particularly pure water, or does it really matter?
I don't think it matters because generally they condense it back and then they'll put it back in again. I'm sure there's some Japanese scientist who's done 50 years of work on water for supercritical steam turbines. I'm not even joking about that. There probably is. So that's steam turbines. So I started out looking at steam turbines, and I was like,
they are fascinating.
Because I got into it from making this video on Westinghouse.
Oh, there's a name that we haven't heard for a while.
I know, Westinghouse. And they were the number 2 in steam turbines after General Electric. A lot of people talked about how steam turbines, like Westinghouse is a failed company, right? They're now CBS. And one of the things that got them so far off their path was in the 70s, they did this real big diversification drive. Right. Where they decided we're going to do everything. They bought elevators, they bought different types of companies. They bought a soda bottler company that actually made money. But like a lot of that put them into huge debt, which then set them on the path to a financial crisis. Anyway, so the thing that was really interesting was why that turbine business didn't do well. And so I was researching it, and I came across people thought that the diversification drive, this move, changed and made it so that they couldn't affect their core business. They couldn't do their core business well. It seemed more to me actually was the opposite. Their core business was failing.
Failing in what way?
More like there was a massive transition after the 50s or 60s where steam turbines needed to get bigger. They needed to get more efficient, because the utilities were buying 2 or 3 of them for each particular utility or for their factory or the power plant. And they needed to get more energy out of them because you can only have so much space. You can only have 2 or 3. And so you need to get bigger. You needed to put these things called reheat cycles. And Westinghouse didn't really have the resources and the manpower and the R&D to really keep up with General Electric. General Electric was kind of managed that transition pretty well.
Because the U.S. demand for electricity was growing.
Yeah, demand were growing. Also, Westinghouse was getting into nuclear energy, nuclear turbines, which are different, actually, very different than normal steam turbines. So, like, it's a very different sort of industry, but they kind of drew them around. It distracted them. And then when they realized they weren't going to win in the Westinghouse, in the turbine industry, that's when they were like, okay, we need to do something else. So it's kind of like it's causation and correlation kind of thing. But anyway, steam turbines for me so that got me into like, how do these steam turbines work and what's going on with them? And I learned that something that blew my mind was that there's a category of supercritical steam turbine, and the supercritical, which is basically when it flashes directly to steam. And then there's a higher category called ultra supercritical, which is when you get the steam heat to something like 550 Celsius. Sorry, I'm going to say Celsius. And that wasn't done for like 20 years. Like they hit it once in, I would say, the 70s or something. And then they couldn't kind of do it.
They couldn't replicate it.
They couldn't replicate it. The turbines at that time literally broke after a couple years. And then they were like, look, we're not going to, the metals keep breaking, so we're not going to do it anymore. And it took the Japanese a decade. It wasn't until the Japanese broke finally with an ultra supercritical steam turbine that actually worked for.
So the issue wasn't hitting the temperature, it was making the metal parts that could sustain that temperature for that many years, constant movement.
Absolutely. That was the key point. There's some design stuff, but like I would say that for the most part, the design has been mostly the same. The working principle is the same. It's the materials have gotten a lot better. It's a materials question. Right. And I think what the Japanese managed to do is that they basically worked their way up the tech tree to build, to create this really special steel. It's a steel that has to be in. I mean, metallurgy. I didn't expect the video to end up becoming like a metallurgy video. I was like, why the heck this has become a metallurgy video?
But in retrospect, it's obvious.
It wasn't. Yeah, retrospect, the metallurgy. Yeah, became that. I got really into metals for a while. So that was the key point was getting the steel right for the rotor, not the blades, the fan blades, but the rotor, which is where you stick the blades in.
Yeah.
Because that has the least insulation.
Oh.
It's always it's deep in the turbine. It gets a lot of heat. So it was fun. It was a fun video. But then I was like, okay, I'm gonna keep working on this. So I moved to gas turbines, which is how we got into this the single crystal stuff. Gas turbines are different from steam turbines because they don't have the water issue. They don't have.
They don't start with liquid.
Yeah, they start with gas and you burn that, and then. But the problem with that is that the gas turbine, so you can get so much hotter, way hotter. But the point where it's like steel can't even handle it anymore. Like you can't use steel. You're talking about 600, whatever number. And so because of that, the blades need to survive these really hotter temperatures. So they started developing these nickel-based alloys. They called super alloys because everything was like Superman back then. But like nickel is one of the most heat-resistant elements out there. Who knew? They created these nickel-based alloys, and then they realized that's not enough, right? Because you need to get even hotter. So what they were like doing was like, we're gonna make this nickel alloy into a single crystal, meaning like there's no grain boundaries.
Joint. Wow.
No grain boundaries. Just like, a semiconductor wafer. If you have a grain boundary in a semiconductor wafer, it interrupts the travel of the electrons or electron holes. That's bad stuff. Well, in this case, having grain boundaries causes more creep or causes something like that.
So the goal is to get a single crystalline structure of a nickel-based alloy so that you don't have any kind of seams or grain boundaries so that it will survive the high temperature, the high pressure, and the spinning for decades.
Yep, literally 2 decades. And I was like, how are they going to do this? Like single crystal. In semiconductors and silicon, obviously you do the Czochralski, right? Like it kind of slowly
It's almost
grows.
easy.
Yeah, it's easy stuff. But how are you going to do that for a blade? And it's brilliant. I don't even know how they figured this out. But it's like you basically grow it out. It's grown, right? And they put a twist in the mold where the mold, because the twist, so when it comes out of the mix, the melt or whatever, there's many different crystals. But then if you it goes through this twist in the mold, this pig's tail, as they called it, and it comes out, and it will slowly winnow out the various different crystals until there's one, and then it just grows from the rest there.
Wow.
It's magic.
And someone just came across that wonderful idea some night and 2 o'clock in the morning or whatever and just said, I know how to do it.
I think it was a single team, maybe it was like a Lockheed Martin or something. And this was like one team that came up with like 3 different breakthroughs in this turbine and in fan blades, essentially. And it was really cool. And then there's other stuff, right? They're not just single crystal stuff. They also have to add like one of the rarest elements on Earth, rhenium, which is actually rare. It's not like rare earths. It's
actual rare. Yeah.
It's a byproduct of a byproduct of a byproduct. They don't make that much of it, and that strengthens it. The blades. It's crazy stuff what they do to make these fan blades, these gas turbine blades. And then they still want to get even hotter than that.
Wow.
It will melt.
Still not enough.
That's still not enough. So what they do is that they drill holes. They have the molds. They have holes in them, so that air flows. They'll take in air from the input. It'll go through the blade, and it'll come out holes on the blade to create a blanket around the blade.
Like an envelope of air.
An envelope of air.
To keep it cool.
To keep it cool at the edge of its melting point.
Wow.
And they add 3 layers of like this special bonding coat to just make this turbine. So this blade,
that little bit more insulation.
Yeah, just a little bit, just to protect it, right? Just to protect it. And it's crazy. I mean, these blades are insane. I was like, when I started out, I was like, why is this so hard? So just a piece of metal. Like, no, it's crazy stuff they do it.
Wow.
And like, it makes no sense that this blade. I mean, this is the very limits of what this stuff, and it does it for 20 years. And
that's the key point, isn't it? 20 years. And it's not like you can, it's down, we'll just climb in and repair it. It's like, no.
Definitely do not, because it's a crap load of money. It's utilization, and it's like, why would you? And obviously,
It would take weeks just to cool it down.
weeks to cool down, and then it's expensive. It's not like you can go in and get a new replacement that fast because you got to grow that crystal blade. I had a really great time looking at gas turbine blades. It's I pull and obviously you know who's the top leader in that. It's the Japanese and the Germans. So they're really good at that.
So gas turbines.
And the Americans, by the way.
The Americans,
They
they've
do
still
that very
got it.
well.
They've
They still got that.
Well, I was going to lead into the other thing that Americans are very good at is jet turbines.
Yeah.
So gas and jet is crossover there
I think it's interesting that like jet turbines came first.
before gas turbines.
Yeah. The jet turbines were like they developed it in the 40s and the 50s, obviously for the war, this war thing that you heard of
Yeah.
that covered the whole world. And then they basically kind of adapted that backwards to a gas turbine.
So what I then want to ask is, so we've got gas turbines. The Americans are also very good at jet turbines. And what I think is fascinating is that we now see videos, jokes online about people getting an old like jet that would go on an aircraft jet and firing it up to make electricity.
Right.
Is that feasible? Like,
Yeah.
that's actually something, it's not just a joke. You could theoretically do that.
Yeah. I don't see why not. I mean, it's the same concept. And also, I mean, jet turbines jet turbines came first. So they kind of work the same way. What I don't know is like how efficient is that going to be, right? Like because it's usually you don't just run the gas turbine by itself. You would have, if you want to have maximum efficiency, you would attach it to a steam turbine. So that excess heat, because you have a lot of excess heat coming out at the end. And so what would be the case is that you would have this combined cycle turbine.
So you're never really doing one alone. You're putting them together in various combinations to get the maximum efficiency out of the heat you've already
62%. And that's like way higher than even the ultra supercritical ones, which is like 48%. And then the gas turbine is like 50-ish%.
So squeezing out every percent is worth it. I mean, that's millions of dollars of
Tens of millions of dollars, for the company. And it's really interesting because I think it's like there's dynamics are different. For these turbines, gas turbines, steam turbines, jet turbines, the importance is the cost of the fuel, right?
Right.
Another video I did, which was the supercritical CO2 video, the turbine video. Different turbine, way different turbine. It's for nuclear energy.
Oh.
And nuclear energy is way different. The economic dynamics are different because the fuel is cheap, or the fuel is so little as compared to the actual cost of building the thing.
Right. Uranium, relatively speaking, because it's once off.
Right. Though Westinghouse once messed up their own. They somehow messed that up too by not buying enough uranium for some of it. But I speak off topic. But these nuclear turbines, they're designed for a different way, and I think because the fuel is cheap, so like they have to be designed for a different set of requirements.
What are the key ones? Obviously, leakage of nuclear material would be one, like radiation. But what else?
Steam. They have to work with a lower quality heat, right? So you have a gas turbine or a steam turbine. You get really hot, right? You can pump it up because it's coal, it's fuel, it's gas, or it's fossil fuel. But nuclear energy doesn't really get that hot. It gets hot, plenty hot, but it's not as hot as a thermal plant. So you have to design for a kind of a wetter, not as hot steel, or not hottest conditions. It's fun stuff.
So it's hot and humid, but not as hot and humid as what you get out of, say, a coal or gas heat.
No, it's more hot, or not as hot, but more humid.
Right, because it's not as hot, right?
Right. So like the gas turbines, they're very dry heat. It's really nice.
Wow, fascinating.
I never expected that turbines would be such a thing.
4 videos so far on turbines. I'm going to foreshadow that we will have one on jet turbines in future because I want to see it and learn about it. And since Asianometry is my encyclopedia of all things that I need to know, I will look forward to that one. Anything else we need to talk about, John? On turbines.
On turbines? No, let's keep spinning them around.
Hot man. This has been a very cool episode of Supply Chain. I'm Tim Colpin of Colpium.
I'm John from Asianometry.